This problem is truly a beautiful problem because, so first of all, what's the problem? The problem is to use Taylor polynomials to approximate. So we want to approximate the integral from 0 to 1 sine of x squared dx. Now what's interesting is if you want to approximate something, you better not be able to have the exact value, because if you have the exact value, why do we want to approximate it? So here the problem is that it's impossible to compute in a closed form. It's just impossible to find this integral, one of these um, impossible to do, like e minus x squared, etc., etc., or sine x over x. That's a class of family of functions that we do not know how to, I mean, we do not know, no, we cannot integrate in a closed form, simple form, okay? So here, so in this case, yes, it does make sense to try to approximate the value of this integral, okay? And again here, let's go back, and we know that the Taylor series of sine x is x minus x cubed over 3 factorial x5 over 5 factorial x7 over 7 factorial, etc. And we know that the domain is plus infinity minus infinity, because the radius of convergence is r equal plus infinity of this. So we have this relation for every x. It's beautiful. So now we know from the theory that we can approximate. So first of all, we need sine of x squared. So this will be x squared minus x squared cubed x6 over 3 factorial plus x squared to the fifth, that's x10 over 5 factorial minus x squared to the power 7, 14 over 7 factorial, etc. And now, so we integrate from 0 to 1, and keep in mind that from 0 to 1 of x to the power k dx, that's x to the power k plus 1 over k plus 1 from 0 to 1, and that's 1 over k plus 1, because 1 to the power k plus 1 is 1, and 0 to the power k plus 1 is 0. So knowing this, we're going to integrate term by term. This is the beauty. Huh? For a power series, you can integrate term by term like polynomials, exactly like polynomials. So we get that the 0 to 1 sine of x squared dx is a series. So the integral of x squared, that will give us 1/3. 6 will give us 1/7, so it's going to be 1 3 factorial times 7, and plus 1 over 5 factorial times 11 minus 1 over 7 factorial times 15, etc. So this integral is a sum of a series. So here, of course, depending on where you stop, I mean, you can take 1/3, but it's not a good approximation, 0.33. But you can also take this one, or this one, or this one, and you keep getting better and better approximations. So for example, if you stop uh, at so for example, 1 over 3 minus the first one is 42 minus 1 over, because it's 6 times 7. The second one is 1320. And the next one is a little bit 75,600. Okay, etc. So if I stop at these, I find that this is equal to 0.3102 minus 1 over 75,600, etc. So I mean, you see, this will be a good approximation, easy to, you have to check, because this one that you are adding at least 3 digits easy, okay? So this will give you an approximation. If you want more decimals, then you will have to add more terms, okay?